Hey folks, this is the second video in a multi-part series of short videos leading to the concept of the tensor product in linear algebra. In the prior video, we looked at the quotient space from a universal point of view. If you're not already familiar with that, be sure to check it out. In this video, we're going to look at another important universal object, the free vector space. Let's get started. I assume you're familiar with the slogan that a linear map is completely determined by its action on a basis. We can express this in a universal way. Let V and W be vector spaces over a field F, and let B be a basis of V, which need not be finite. The slogan tells us that for any function f from B to W, there's a unique linear map phi from V to W, which agrees with f on B. In other words, which extends f from B to all of V by linearity. Here's the diagram. The arrow on top is the inclusion function from B to V. The map phi is defined like this, where the sums are finite. It's easy to see that this is the only possible definition. If phi is linear and extends f, then it must be defined in this way. On the other hand, it's also easy to check that this definition does give a well-defined linear map which extends f. This means that the inclusion function from B to V is universal among all functions from B to W by way of linear maps, and that's true for any W. Here we started with a vector space V and then fixed a basis B, but what if we turn things around? For an arbitrary set X, is there a vector space Fx and a function from X to Fx, which is universal among all functions from X to vector spaces W by way of linear maps, all over the field F? From what we just saw, this is equivalent to asking if there's a vector space Fx with basis X over F. Clearly, such Fx will be unique if it exists. But does it exist? Intuitively, since X is a basis, Fx should consist of all formal linear combinations of elements in X over F. Formal here means that we're talking about the syntactic expressions themselves. There's no pre-existing addition and scalar multiplication. Addition and scalar multiplication should then be defined to make this work as expected. The elements of X will then form a basis for Fx over F. Indeed, they'll clearly span, and they'll be free of any non-trivial linear relations over F, so they'll be linearly independent. Of course, this is just a guiding intuition, not a rigorous definition. To get a rigorous definition, we observe that such a formal linear combination is completely determined by the coefficients corresponding to the elements of X. Therefore, we actually take Fx to consist of all functions from X to F with finite support, that is, functions which are non-zero for only finitely many elements in X. We can think of each function as picking out the coefficients of a formal linear combination. Addition and scalar multiplication are then induced from F pointwise. In this way, we obtain a vector space structure on Fx. Fx is called the free space on X over F. What about a basis? For an element X in the set X, consider the function Fx, which is 1 at X and 0 elsewhere. This function is clearly in the free space since it's non-zero at only the one element X. Moreover, it's easy to see that these functions form a basis of the free space. I encourage you to pause the video and verify this yourself. In doing so, you'll see how in the free space, the formal linear combinations from our intuition become actual linear combinations of these functions. The function from the set X to the free space, which sends each element X to its function Fx, is injective, so we may identify each element with its function to make the set X itself a basis for the free space. That's exactly what we wanted. Like in the prior video on the quotient space, a major point I want to convey here is that from the universal point of view, these implementation details of the free space aren't super important. They show us that a universal object really does exist, so they serve a purpose, but beyond that, everything we need from the free space we can get from its universal property. Now let's look at some examples. Taking the field to be the real numbers and the set X to consist of the numbers 1 to n, the free space is isomorphic to Rn. This is easy to see from the universal property. For instance, the function sending I in X to the ith standard basis vector in Rn extends to an isomorphism from Fx to Rn, which maps X to the standard basis. As another example, the space Fr2 over R consists of all formal real linear combinations of pairs of real numbers. It's really important to see that this does not involve the ordinary vector space structure on R2 in any way whatsoever. We're just using R2 as a set of pairs here, not as a vector space. For instance, in the free space, the pair 0, 0 is not the zero vector. After all, the pair 0, 0 is a basis vector, so it can't be 0. The pairs 1, 0 and 2, 0 are linearly independent, so in particular the pair 2, 0 is not 2 times the pair 1, 0. Similarly, the pairs 1, 0, 0, 1, and 1, 1 are linearly independent, so in particular the pair 1, 1 is not the sum of the pairs 1, 0, and 0, 1. Remember, the pairs in the set R2 form a basis of the free space, so non-trivial linear combinations of them can't be simplified. This is probably the biggest confusion about the free space, so make sure you really understand this before continuing. Since the free space does contain all the pairs in R2, a natural question is, can we somehow recover the ordinary vector space structure on R2 from the free space? The answer is yes, and it follows from the universal property. We can define a linear map phi from the free space to the vector space R2 by mapping the basis pairs to themselves. Notice that phi just extends the identity function on R2. Now, phi is surjective, so if K denotes its kernel, then the vector space R2 is isomorphic to the quotient space FR2 mod K by the first isomorphism theorem. From our prior video on the quotient space, we know that phi is here imposing new relations in the free space by killing off K in order to obtain the vector space R2. What are those relations? It can be shown that K is spanned by the vectors seen here. By forcing these vectors to become 0, phi recovers the ordinary vector space structure on R2. If you study the vectors carefully, you'll see why this happens. By forcing these vectors to become 0, phi effectively forces the vector space operations from the free space to agree with the vector space operations from R2 in the resulting quotient space. More generally, this diagram commutes for any vector space V. Here the line on the left is the identity function on V, and the first arrow on top is the inclusion function from V into the free space on V. Phi is the linear map induced by the universal property on the free space and is surjective. Pi is the canonical projection onto the quotient space by the kernel of phi. Phi bar is induced from phi by the universal property of the quotient space and is an isomorphism. This shows that any vector space can be recovered from a free space by taking a quotient. Of course, if we're willing to choose a basis B of V, then V is isomorphic to the free space on B, and we don't need to take a quotient. We note two additional facts before wrapping up. First, if f is a function from x to y, then it induces a unique linear map phi from the free space on x to the free space on y, making this diagram commute. The vertical arrows here are the inclusions. This follows from the universal property of the free space on x applied to the composite arrow going right and down, and it shows that the free space construction acts on arrows, not just objects. This action on arrows is well behaved. For example, it's easy to check that it maps identity arrows to identity arrows and maps composite arrows to composite arrows. Finally, the free space on a disjoint union of sets is just the direct sum of the free spaces on the sets. Here we're using the square cup symbol to denote disjoint union. This result also follows from the universal property, or equivalently from the observation that the disjoint union is a basis for both spaces. It comes in handy when working with free spaces. In summary, we've seen in this video that the free space is the universal way to construct a vector space from a set. We've also seen that any vector space structure on a set can be obtained from the free space by forming a suitable quotient space, which we know amounts to imposing relations in the free space. Finally, we've seen that the free space construction is well behaved with respect to functions and disjoint unions. The ideas from this video will be useful in our study of the tensor product in the upcoming videos, so stay tuned.